Okay, welcome back to grade 9 Applied Mathematics, continuing our work in Unit 9. This is going to be lesson 2. We're going to be looking at the sum of the interior angles of a polygon. Now, remembering that you don't have a physical copy of the notes because we're unable to get those printed, you might want to follow along on maybe an electronic copy if you have an iPad or something, or if you have a printer, you could print them. If not, just have a blank piece of paper out beside you and maybe attempt some of the questions as we're going along. All right, so sort of a recap. See what you know. See if you can figure out what the values of x and y are in these pictures based on the work that we were doing yesterday, our first time to ponder pause. All right, so resuming to take this up. So the first thing I've highlighted here in green is those are opposite angles, and they'd have to be equal to each other. So I do know that y is 110, so I know that one can't be right, and I know that that one can't be right. Now, to determine whether A or C is the correct answer, I'm now going to have to find angle x. And I do know that there should be 110, not 110, I'm writing 110 there, but the sum of the interior angles in a triangle is 180. So what angle measure would I put there? So if I put so this one is not the correct answer. This one is the correct answer, because 55 plus 35 plus 110 is not 180. But if we put a 35 in here, 35 plus 35 is 70, plus 110 is 180. So the correct answer was A. All right, moving forward, just recapping some things. 360 degrees in a complete revolution of a circle. How many degrees in a semicircle? Again, a time to ponder pause. Taking this up, it's a half a circle, so we expect it to be half of 360, which happens to be 180 degrees. Recall yesterday, I asked you to mark out the vertices of a triangle. I asked you to tear them off, and then they lined up in a line, right? They became linear. I'm going to emphasize the word straight here, even though in math, if you say line, it does mean straight. A curve is bent. They made this straight angle. Notice there's a half a circle revolution there. So that's how we determined there were 180 degrees, would be the sum of the interior angles in a triangle. So thinking about what do you think would be happening with a quadrilateral? Do you think that would still be 180 degrees? How many triangles do you think it would take to create one quadrilateral? So I'm going to take a time to ponder pause for you to think about this. Do you think it would make sense for those 4 interior angles to add up to 180 degrees, or do you think it should be greater? Again, a time to ponder pause. All right, so resuming and taking this up, and let's just undo that for a sec. I need the arrow and not the pencil. Sliding that, so do you see how we're splitting and creating a triangle? I want to stop right there. So we split and we create a triangle. We joined these two vertices. We created a triangle. The angle that was there we brought down to here. The angle that was there we brought down to there. So there's 180 degrees. And now what are we going to do off the second triangle? We're going to rotate those two angles up there. And now we've created a second 180 degrees. So we were able to sort of, I don't want to use the word bisect, because bisect would imply those angles, those triangles were equal, and they're not. We were able to split this quadrilateral into 2 triangles. The sum of the interior angle in each triangle was 180, and 180 plus 180 is 360. So we needed 2 triangles to do this. I'm going to get you to think about, let's move to the next slide. How many triangles do you think would be needed to create each of the polygons there? And then what could you conclude about the sum of the interior angles of your polygon? And again, we're going to take a time to ponder pause. Okay, resuming. So if we were meeting face to face, we would probably have these sitting out in front of us, and we would be thinking about maybe tearing the vertices off like we did the previous day and seeing where we can go from there. We can't physically do that here. So we just looked at the quadrilateral. This one's a pentagon. It has 5 sides. Now, how many triangles could we split this one into? So let's start moving. There's our first triangle. The angles that we split came down there, so there's 180 degrees for the first triangle. Let's split. Notice how we're splitting and moving over there. There's the second triangle, so we have another 180 degrees, and continuing to slide, there's our last triangle on the top. So we were able to split the pentagon into 3 triangles. The sum of the interior angles in each triangle is 180. So 180 times 3 is 540. So it looks like we would expect the interior angles in the pentagon there to be 540. Let's look at this one. This one is a hexagon. It has 6 sides. And again, how many triangles can we split it into? All right, there's the first triangle, 180 degrees. There's that second triangle. We're now up to 360 degrees. There is the third triangle. We're at 540. The fourth triangle, well, we are now at 720. So we could split a hexagon into 1, 2, 3, 4 triangles. Let me just pull this one over so we can see them. So, whoops. There is 1 triangle in a triangle. There are 2 triangles in a quadrilateral. We can create 3 triangles in a pentagon. We create 4 triangles in a hexagon or a 6-sided figure. And this is a heptagon, 1, 2, 3, 4, 5, 6, 7 sides. How many triangles do you think we could split this one into? And then we have an octagon there. How many triangles there? So I'm going to do a time to ponder pause just for you to think about that. And let's resume and take this up now. How many triangles could we split this into? There's the first one. There's the second one. There's the third one. There's the fourth one. There's a fifth one. So splitting a 7-sided figure, which is a heptagon, into 1, 2, 3, 4, 5 triangles. So the sum of the interior angles here would need to be 180 times 5. All right, what about the octagon? How many triangles can we split that into? So there's the first one. There's the second one. There's the third one. There's the fourth one. There's the fifth one. And there is the 6th one. So we are able to split this up into 6 separate triangles, 1, 2, 3, 4, 5, 6. And the sum of the interior angles in an octagon would need to be whatever 180 times 6 is. All right, so back over here, what I would like you to do, if you were able to print that note or if you have an iPad in front of you, is physically split these into the correct number of triangles. Again, a time to ponder pause. All right, resuming to take this up, hopefully you drew something similar to this. What you do is you pick one vertex and you join it to the other vertices. So I'm going to show you on this particular one here. See if I can delete those 2 lines. I'm going to try it from another vertex. So let's say it was this vertex. So I'd need to connect to there. It's already connected to this vertex, and then I would connect to that one over there. And that's an alternate way to split this into the 3 triangles. So pick one vertex, whatever vertex you want, and then connect it to all the other vertices. This one was one of the sides. Connect to that vertex, connect to that vertex. And connecting to this vertex is a side on the polygon. So we can split this into 3 triangles. This one is split into 3. This one has been split into 4. Each of the quadrilaterals were split into 2. So now what you're going to do is you're going to drag these to where you think they belong. Which shape has the sum of the interior angles of 180? Which ones are 360? Which ones are 540? Which ones are 720? Again, a time to ponder pause. All right, resuming, and I'll just show you where the answer should be. The triangles belong here. The sum of the interior angles of a triangle is 180. Quadrilaterals belong here because we can split them into 2 triangles, and 180 times 2 is 360. Each triangle, sum of the interior angles 180. If we take a look at our pentagons, each pentagon can be split into 3 triangles. So 180 times 3 is 540, and then each hexagon can be split into 4 triangles. And 180 times 4 is going to be 720. So if we want to figure out the sum of the interior angles of any polygon, we really need to figure out how many triangles we can split it into. So I'm going to move to this next little thing here. And I'm going to open this GSP sketch. There we go. And I'm just going to show you what happens as we increase the number of sides. So there's the quadrilateral split into 2 triangles. There's the pentagon split into 3. There's the hexagon split into 4. There is the heptagon, or a 7-sided figure, split into 5. There is the octagon split into 6. Now momentarily I'm going to move this to 10. How many triangles do you think a 10-sided decagon, 10-sided figure, how many triangles could we split that into? All right, and if you need more time to think about it, please feel free to pause. So I'm going to go to 10 sides now. And we're 1, 2, 3, 4, 5, 6, 7, 8. What if I were to move this to 20 sides? How many triangles would we be able to split a 20-sided polygon into? And again, if you would like more time, feel free to pause yourself. I'm just going to start moving forward and doing that. 12. There we are at 20 and counting. They're very tiny now. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, another one there, 18. So we were able to split it into 18. Again, the more sides we add to this, another thing I'd like you to notice, the more circular it becomes, and then it becomes very difficult to see all of the triangles we are creating, because some of them are right in here and they're very tiny and we can no longer see them. So bringing it back down, these are the triangles I'm talking about. Those ones there are becoming harder to see. All right, back to the note now. Now that we've seen it's possible to split them up, so you're going to start completing the chart. I would like you to complete the chart all the way out to here. So I'm going to draw a line across like that. So record the number of sides, the number of triangles it could be split into, and record the sum of the interior angles. Again, a time to ponder, pause. All right, resuming to take this up. This was a 3-sided figure. It is just one triangle. The sum of the interior angles 180. We talked about splitting a quadrilateral into 2 triangles. 180 times 2 is 360. I put 4 minus 2 there. We're able to split a pentagon into 3 triangles. And so 5 minus 2, 3 triangles. 180 times 3 is 540. And then we were able to split this one into 6, not 6, but 4. We started with 6 sides, and we were able to split that into 6 minus 2, or 4 triangles. 5 minus 2, 3, 4 minus 2, and so on. The heptagon was split into 7 triangles, and note that 7 minus 2 is 5. The octagon was being split into 6 triangles, and notice that 8 minus 2 is 6. So some of the interior angles, 180 times 6 is 1080. Forgot to note this one, 180 times 5 is 900. 180 times 4 is 720, and 180 times 3 is 540. When we jump out to the 10-sided, we knew there were going to be 8 sides, and 180, 10 minus 2 gives us our 8, not sides, but triangles, 8 triangles, and 180 times 8 is 1440. So now you're going to think about this one. We're not going to draw it because it would be very difficult to draw a 20-sided figure. It'll start to look like a circle. How many triangles will we get? See if you can follow the pattern in the chart. How many triangles are you expecting to get? And then what would be our total sum of the interior angles? Again, a time to ponder, pause. All right, resuming. So we're getting 18 sides, and notice that the relationship between the number of sides and the number of triangles is they're always off by 2. 2 separating these, 2 separating 2. They're always 2 apart. So if I want to find the number of triangles, I can simply take 2 away from the number of sides. So 20 minus 2 is 18, and 180 times 18 gives me 3240. Now we're going to generalize because we do need the formula. And again, I want to draw to your attention the relationship. How do you find the number of triangles? You have to subtract 2 from the number of sides, and in this case we don't know what it is. So you're going to need to write an expression here that reflects the fact that you understand you should take 2 away from it. And then how do we find the sum? We do 180 times the number of triangles. And we found the number of triangles by taking 2 away from the number of sides. So again, a time to ponder pause so you can fill that in. Resuming, hopefully you took time to think that one through. Come over here and I'll show you what the answer should be. So if there are n sides on the triangle, there would be n minus 2 triangles. So n sides on your polygon, I do believe I said triangle, but n sides on your polygon, there will be n minus 2 triangles. You can split it into that many triangles, and again, that's following our pattern. 4 minus 2, 5 minus 3, 6 minus 4, just one triangle here, and we notice that they're 2 apart all the way down, 2 apart. So these would be 2 apart, or the other way to look at it is the number of triangles is always 2 less than the number of sides. So take away 2 from the number of sides, and then we're then going to multiply that by 180. And this is the formula we're then going to use. So how do you find the sum of the interior angles in any polygon? We use this formula right here. So a big summary slide over here. The sum of the interior angles in any polygon with n sides is this, the formula we just derived, 180 degrees times n minus 2, because n minus 2 gives you the number of triangles. That's what I'm noting right there. So a hexagon is comprised of 4 triangles, 6 minus 2 being 4. The sum of its interior angles is 720. And here we have our 6 angles, so I'm showing you now that adding those 6 angles together, we would get 720. And again, how do we know it was 720? Because we can split it into 4 triangles. All right, so we spent a good deal of time, about 16 minutes now, just developing the math. You tend to be a better math student if you develop the formulas and theorems on your own rather than having the teacher tell it to you. So these will now be 2 applications of the theorems. So you're going to have to look at this. Do you remember how many degrees the sum of the interior angles of a quadrilateral? If you've forgotten, this is why I went over the triangle bit. Imagine how many triangles could you split that into. That will give you the sum of the interior angles. Again, a time to ponder pause. All right, resuming to take this one up. I'm just showing you that we could split it into 2. So if I've forgotten what the total number of degrees would be, just showing you that I could split that into 2. And from here, if we can split it into 2, we would know what the total sum is. I'm just going to pause for a sec. All right, so I'm going to resume. I didn't want all that information to be there. I'm just talking about knowing that we can split this into 2 triangles, so the sum of the interior angles would be 360. And now you're going to work through that. The sum of 1, angle A, plus 82, plus 51, plus 113 should be 360. Now we'll do a time to ponder pause for you to give me the answer. All right, resuming and moving forward. As we mentioned, the sum of those 4 interior angles would need to be 360 degrees. 82 plus 51 plus 113 is 246. So isolating for A, we'd have to do 360 minus 246, and that's going to give us that A is 114 degrees. Now you're going to look at this new figure here. Find the measure of the missing angle. Well, that missing angle is right here. Pick a letter for it. Let's call this one B. How are you going to find the angle of measure B? Note, these are interior angles. So what is the sum of the interior angles on this figure, which has 5 sides? Again, if you don't have it memorized, if you've forgotten, I would start by deciding how many triangles can you split it into. Again, a time to ponder pause. All right, resuming, we can see that we can split this into 3 triangles, so the sum of the interior angles should be 180 times 3. And then you would know that the sum of this angle, angle 2, there's angle 3. Don't forget to include this one. You should know what the measure of that one is. Plus this one. If you add those 5 together, you should get 180 times 3, which is 540. A final time to ponder pause for you to finish this off completely. All right, resuming. So B plus 90 plus 111 plus 103 plus 122, all of that should be 540 because a pentagon is comprised of 3 triangles, and 180 times 3 is 540. 90 plus 111 plus 103 plus 122 is 426. And in isolating for B, we're going to need to do 540 minus 426. That gives us 114. So the measure of angle B is 114. All right, so if we were meeting in class, we would have seen that the bulk of this lesson was just the derivation of that formula. I've shown you 2 applications on how to apply it, and there would be more questions in the homework. And then we also would have given you this exit slip. What would be the sum of the interior angles in a 15-sided polygon? And write appropriate measures for the interior angle of this pentagon. So I'm going to suggest, if you want to try the exit slip, pause now, and then what I will do is give you reasonable answers for both. So we'll take another time to ponder pause. And resuming. So we know that a 15-sided polygon can be split into 15 minus 2 triangles. So that's the number of triangles. And we know that each triangle has a sum of the interior angles of 180. So I need to do 180 times 13, and 180 times 13 gives us 2340. So the sum of the interior angles of a 15-sided polygon would be 2,340 degrees. Now, writing appropriate measures. How would this work in class? So what I would be looking for is, this is clearly obtuse. If you put 60 there, I would mark it wrong because 60 is an acute measure. So wherever we see an obtuse angle, I'm looking for an obtuse measure. When I see an acute angle, I'd be looking for an acute measure. This one looked like it was close to 90, so I just decided to call that 90. So then I went through and said, that's 90, and then imagining sort of where 90 degrees would have been over here. So let's say 90 is approximately there. And then I'm gauging roughly what I thought that would be. I felt 115 would be appropriate here. This angle looked a little bit larger to me, so I called that one 125. And then this one looks like it was larger than both of those, so I called it 135. Now, I cannot randomly assign a number here, because I do know that the sum of the interior angles of a pentagon is supposed to be 540. So these were the angle measures I chose. I chose to call this one 90. I chose to call this one 135. I chose to call that 115. And I chose to call this 125. I add all of those up, and the total that should give me is 465, not 450. And then I now know this angle here, to make sure everything adds to 540, should be 540 minus 465. That gave me 75. And then you just do a reasonableness check. If this was coming back as an obtuse angle or 90 degrees, it clearly doesn't look like it's 90 degrees, then you can just go and change these values up so that you get a reasonable answer there. So that's what we'd be looking for in a question like that. We're looking for you to put reasonable numbers there and then recognize that all of those angles need to add up to 540. All right, that brings us to the end of this lesson, which was on the sum of the interior angles of any polygon. We developed our little formula there. That was 180 times n minus 2. If you want further practice, I'm going to suggest you do some of the homework from the book. We're now at the end of our lesson. If you made it to the end, once again, thank you for watching. Don't forget to like and subscribe, and as always, take care and stay safe.